Okay, so it's 11. Let's get started. So today we will start a new chapter called motion. In this chapter, we will talk about one-dimensional motion, meaning motion of an object in a straight path, okay, straight line. So let's first define what is motion. So what do you guys think is motion? Movement, okay, yeah. Object in movement, okay. So when something is moving, it's in motion. That's the everyday life definition. But in physics, in order to define motion, we need to compare an object with something. Okay, that something is called a reference point. So without the reference point, we won't be able to define motion. So motion is defined as basically the change in the object's position with respect to some reference point. Change in an object's position. It could also be orientation. Okay, with the passing of time. For example, let's say I am standing at some point near the wall. Okay, so this is the wall. That's the wall. And I'm standing somewhere here, and I change my position with respect to this wall. So in 1 second time, I change my position from here to here, and in the next second time I'm here, and in the next second time I'm here. So you see, as the time passes, my position changes from here to here, from here to here, here to here, with respect to the wall. So initially, that's the distance between me and the wall, and then next time that's the distance, next time that's the distance, that's the distance. So you can say that I am in motion with respect to the wall. Okay, you also need to say with respect to wall. If the wall itself is moving along with me, then I am not in motion with respect to wall. I am at rest with respect to wall. Okay? For example, I have this chair as a reference point. Okay? So that's the reference point. If I move to my right, I am in motion with respect to the chair. But the chair is itself moving with me like this. Okay? Then I am not in motion with respect to the chair. Okay? I am at rest with respect to the chair. So when you define motion, it depends on what reference point you are choosing. Okay? What's your reference point? So for example, we are in motion with respect to a star, but we are at rest with respect to the earth, because we are on the earth and we are moving along with the earth. So earth and we are both in the same motion. So with respect to earth, we are not in motion. And the path along which an object moves is called trajectory. Okay. If I throw something in air, so the object will follow some trajectory. Okay, so I will follow a path, and this path is what we called trajectory. Okay. Now, what kinds of motion you guys know? from your everyday life experience, you see different kinds of motion. Like the motion in which you are moving at constant speed, okay, which is called uniform motion. Uniform motion is when you are moving at same speed all the time. And you have non-uniform motion when you are moving at different speed at different times. So you can say speed is changing. Changing means it could be either increasing or decreasing, okay? Now, in non-uniform motion, two things can happen. Okay, one is you are changing only the speed, meaning, let's say you are moving at 10 miles per hour, and then in the next instance, you are moving at 20 miles per hour. Okay, you change your speed, how fast you are moving. Another way you can execute non-uniform motion is by changing the direction. Keep the speed same, but change the direction. Okay, for example, you are moving in a circular track. You are moving at constant speed. Okay, so let's say you are moving at 20 miles per hour. Everywhere, it's 20 miles per hour. Everywhere, it's 20 miles per hour. 20 miles per hour. But you are changing your direction at each and every point on this path. So here, at this point, you are moving along this path, okay? That's the direction. At this point, your direction would be pointing this way. Here, it would be pointing this way. So the direction of your motion would be tangent to the circle at each and every point. That means your direction is changing. Or sometimes it could be combination of both. You can change both speed as well as direction. Okay, you can change both the speed and direction. So let me show you how we represent all these different kinds of motion. So one of the main objectives of physics is to represent physical phenomena in some kind of picture, okay, or diagram. So here is the diagram for different kinds of motion that we just discussed. The first one is constant speed. When you want to represent constant speed, what you do is you draw the pictures at the equal interval. So these are the snapshot pictures taken at equal interval of time. So let's say this is taken at 0 second time, this is taken at 1 second time, 2 second time, 3 second time, and each interval of time you cover the same distance. So you cover this much distance. Oops. So who is that? So you cover same distance in each interval. So that's the distance, that's the distance, that's the distance. So same distance in same interval of time is uniform motion. Okay. Whereas here, you see initially in 1 second time you cover this much distance. In the next second you cover even more distance. In the next second you cover even more. So your displacement or your distance is increasing with the time. How much distance you cover is increasing with the time. So that means you are speeding up. Okay, that's how you represent speeding up. Slowing down, you see this car. Initially, it covers this much distance in 1 second. In the next second, it covers less distance. and in the next second it covers even less distance. Okay, so the distance is decreasing. So this is slowing down. Okay. Now, I'm not a very good artist. Okay, I don't want to draw this real diagram. So instead of drawing this real diagram of a car or a person, I can just use something called particle model. Okay, what that means is, in physics, we can represent any object by a dot mark called particle, such that we assume that all the mass of that object is concentrated at that particle. Okay, so we use the particle model to represent an object. So this is a simplification of in which we treat a moving object. It could be moving or something that could be at stationary, that is not moving. We treat a moving object as if all its mass is concentrated at a single point. Okay. So for example, I have this object. Using the particle model, I can represent this with a dot mark, okay, dot point. So that's the representation of this object. And when we do that, we assume that all the mass, so mass is distributed everywhere here. Okay. There is mass, a little bit of mass here, there's a little bit of mass here, a little bit of mass here. We assume that all those mass were concentrated at this point. Okay, that's the particle model. So let's see. So here is an example. So we have car moving on the road, and we can represent this car by these dot points, okay, dot marks. These are the particle models. So let's try to answer a question for our previous discussion. So we have car A and car B. Their motion are shown on the picture, and the pictures are taken at the same time interval. So that means starting at 0 time, you took this first picture at t equal to 0, and then at t is equal to 1, you took this picture as well as that picture, 1, and at t is equal to 2 seconds, you took this picture. Okay, so these are all times. So that means which car, either A or B, is going slower? A. Why is it A? Yeah, exactly. So in 1 second, it covers this much distance, whereas in 1 second, this car B covers that much distance. So more distance, less distance in same time interval. So this is moving slower. Okay. Now let's talk about two very important terms. Let's see if I have more questions. Okay, let me ask you one more question, and then we'll move on to the next one. So we have two runners jog along a track. Okay, let me first introduce the term, and then I'll come back to this one, okay, because I need to introduce the term first. So the next term that we need is position and coordinates. Coordinate system. So like I said before, in order to specify my position, I need a reference point. Okay? To specify the position of an object, we need a reference point. And when we represent the object's position, we represent that in a number line. Okay, it's just like in the math, you have this line representing a bunch of numbers, like starting from 0, 1, 2, 3, 4, like that. This is called origin. Okay. So in order to specify the position, we take or we represent the reference point by this origin, 0 mark. So reference point is considered to be 0 mark. For example, if I want to measure my position with respect to the chair, so the chair would be considered as the 0 mark. Okay? And then how far I am moving from the chair would be these numbers. Okay? So we need reference point, okay, and we also need to know how far I am from the origin. So I need to know the distance from the origin. And also, not just the origin and how far I am from the origin, I also need to know which way I am moving. Okay, I also need to know the direction. Which way I am moving with respect to the origin. So by knowing these things, we can specify my position, where I am. So if someone asks you, where is a particular star located? You cannot answer that. Okay? First, you need to know the reference or origin. What's the reference? Do you want to measure the star with respect to the Earth, or you want to measure the star with respect to some other star, or with respect to sun? Okay? So you need the origin first. Okay? And once you have this origin, O, and then you can say this star is, let's say, 100 or 100 million miles from this point. Okay? And you can also say this is to the right of this star. So like I said before, the combination of the origin and an axis marked on both positive and negative directions make a coordinate system. So not just the positive numbers, we have positive numbers here. We also need to write the negative numbers, because sometimes I may be moving to the right of this origin, or sometimes I may be moving to the left of the origin. If I move to the left of the origin, then it is indicated by these negative numbers. So let's say if I move to the right, you can say I am positive 1 meter from that. If I move to the left, so you will need to say I am negative 1 meter. Negative means to the left. Positive means to the right. Okay? So this thing is called coordinate system.
So
Yeah.
like left and right is so subjective.
Mm-hmm.
left is different than my left right now.
Yeah, so when we talk about left and right, we talk with respect to the origin. So yes, you are right. So for you, your left would be that way. So for you, yes. If I move this way, then for you, it's negative 1 meter, negative 2 meters. But it depends on observer to observer. Yeah, you're exactly right. So measurement is totally subjective. For me, it's positive 1 meter, but for you, it's positive negative 1 meter. It's not fixed. So it depends on who is measuring the position. Okay. So that's why we have this subject called relativity. Relativity is nothing in the universe is absolute. Everything is relative. Depends on who is measuring, or measuring with respect to what, right? All those things. So like you have this object. So how big is this object? You cannot answer that, right? You need to compare that with something. So if you are measuring this with respect to this, it's a bigger object. But if you are comparing this with this, then this is a smaller object. So it's all comparison. Physics is all about comparing the physical phenomena with something else. Okay, so sometimes when we talk about where I am, I represent my position by a symbol, okay? And that symbol is x. When you see this small x, this is asking me where I am, okay? So this is symbol for position. So instead of writing all these numbers, you can just say, you can just represent that by x. X is like a placeholder, okay, like a basket. So that will accept the value based on where you are. Okay, it's a variable. So that's about the representation of motion. And when we represent the motion, we also need to talk about time. Okay? Because time also plays a very important role in defining motion. So let's put that. So time. So for a complete motion diagram. So I showed you how to represent motion on a line. Okay, so we have 0, bunch of positives, bunch of negatives, and I can say I am here, that's my position. But if I want to know how fast I am moving or whether I am moving or not, I also need to bring time in this picture. Okay, so for a complete motion diagram, we need to label each frame, okay, with its corresponding time. T as read-off clock. What that means is, so at one instance I am here, and in the next instance I am here, in the next instance I am here. Okay. Just by saying instance, that does not quantify my motion. So I need to say at exactly 1 second time later I am here. Okay, this is 1 second time later. In the next second I am here. In the next second, I'm here. Okay? If I use the time, then I can quantify my motion. That's why I need to also write the time for each of these instances. When, at what time I'm here, at what time I'm here, at what time I'm here. Okay? So that's why we need the time. Okay, let's go back to the question from the PowerPoint. Okay. So we have the two runners, A and B. They are represented by the particle model. So we are not drawing the actual picture here, just drawing the particles. And each of the picture or each of the dot is the position in 1 second time interval, meaning this picture is at 1 second, this is at 2 second, this is at 2 second, this is at 3 second, this is at 3 second, this is at 4 second, 4 second, okay, and at each second time. So which runner is moving faster, A or B? Yeah, so that's obviously A. So you just need to see the distance travel in same time interval. So in 1 second, A travels this much distance, whereas in 1 second, B travels this much distance. So A travels more distance in the same time interval than the distance traveled by B, so A is moving faster. See. Oh, okay. That's, I already showed you the question, but here, let's see this question. So for A and B, so which one is moving faster between A and B? So we see this is 2 seconds from here to here, and this is also 2 seconds from here to here. Same distance in same time interval, right? So don't confuse between this point and this point, and this point and this point. So this is taken in 1 second interval, whereas these are taken in 2 second interval. So you just, when you compare the speed, you need to see the distance traveled in same time interval. If you compare in 2 second time, from here to here is 2 second. Here also you need to compare, see how much distance is covered in 2 second time. Okay, so it seems like they travel same distance in 2 second time interval, so they are traveling at same speed. Okay, so these are fundamental things that you need to understand to understand the higher conceptual understanding. So next thing is position and displacement. Or change in position and displacement. So we talked about position and we talked about coordinates. So here we have a car and a cow. Okay, so we are locating this car and the cow with respect to the origin. So in this case, our reference point is the post office. Okay, this is the reference point. So whenever you are talking about the reference point, we denote that by this origin, 0 mark. Okay, that's our reference point. Okay, and then with respect to the reference point, the car is 4 miles to the east or to the right. Okay, whenever it's to the right or to the east, we put plus sign in front of the number. Plus sign means it's to the right. Okay, here the cow is 5 miles to the west or to the left of the origin. So that negative sign means left. Okay. Now when the car is moving, the car will be at some other location, okay, after some time later. So sometime later it would be here. So that means the car changes its position. Okay, it goes from, it starts at 4 and then it reaches 5 or 6 or something. So it's changing the position. So in physics, the change in position is called displacement, okay, which is one of the important physical quantity. So displacement it is the change in position of an object. Okay. So initially, let's say you are at this position. Initial position, we know position is denoted by letter x. Okay. If it is initial, we write the subscript xi. Okay, subscript I. And after some time later, your position is here. Okay. So position is denoted by x, and its final position, so denoted by x sub f. So change is denoted by this delta symbol. Whenever you see this delta symbol, it is indicating that it's the change. Okay, change in x. So displacement is change in x. That is final minus initial. Whenever you see the word change, change means final minus initial. That's always true. Okay. So that's the formula for displacement. So in this particular example, what is the displacement of this object from this point 1 to point 2? So delta x is final position. Final position is at 2. Okay, let's say 2 meters, and initial position is at 1. So 1 meter. So the displacement is 1 meter. Now, if there is nothing here, that means there is a positive sign, and this positive sign indicates that you are moving to the right. Okay, the direction is to the right. Let's see if I have a question. Okay, here is a question. So Carol is enjoying a bicycle ride on a country road that runs east-west past a water tower. Define a coordinate system so that increasing x means moving to east. Okay, moving to east means the positive, and moving to west means negative. And water tower is the reference point. We are considering our reference point to be the water tower. So what's her displacement during the half-hour time? So when you deal with this kind of problem, first thing you need to do is draw the picture. Okay, draw the diagram. First thing is you need to draw the coordinate system. Coordinate system is a line with the numbers, with the origin mark. Okay, so here is the coordinate. Our coordinate is the origin as the water tower, and left side is negative mark, a negative distance, and right is positive. Okay, so that's the starting point. That's what it says. So she starts 3 miles east of the water tower. That's the starting point. And then in half-hour time, she would be 2 miles west of the water tower. So 2 miles west means negative. So that's our final position. So xi is 3 miles, and x final is negative 2 miles. Okay. And again, the measurement is always with respect to the origin. I'm measuring from the origin. So delta, we are asked to find delta x displacement. Delta x is x final minus x initial. X final is 2 miles or negative 2 miles. And x initial is, we have minus sign here, plus 3 miles. Okay, so negative 2 minus 3 is 5, and you need to write the unit also, 5 miles. Okay, minus 5 miles. Minus sign means she will be moving to the left. Okay, so that means it's left. So sign is very important. It tells you which way she is moving. So that's the displacement. Now, in physics, we often talk about how fast something is moving. So when we quantify how fast something is moving, we also need to bring the time into consideration, okay, or change in time. So change in time. So a time interval denoted by delta t measures the elapsed time as an object moves from its initial position to final position. Okay, or moving from xi to xf, how much time it has elapsed. That's the change in time. And this elapsed time, delta t, is always positive. Time is never negative, it's always positive. Always positive. Okay. So with that, now we are in position to define speed. We can now say how fast something is moving. So how do you define speed? We use the term speed all the time in our everyday life. So what is meant by speed in our daily life? That's the mathematical form. So that's some. It's right. Okay, it's not completely right, but it's partially correct. So how do you define it qualitatively or conceptually? Just in like layman term, how do you define speed?
How fast you're going.
Yeah, exactly. So how fast you are moving. So whenever you see this word fast in physics, we use the term rate. Okay, we call this rate. And moving means changing position. So the formal definition of speed is it's a rate of change of position of an object, meaning how fast you are changing the position. Okay. So that's the origin, how fast I'm changing the position with respect to that. That's my speed. Okay, this motion versus this motion. The first one is changing the position faster. That means my speed is faster in the first instance, okay, or in this dot diagram, or the particle diagram. We can write this as, so 0, 1, 2, 3, 4, -1, -2. So we have this point versus this is A, this is B. So we see that B is changing its position faster than A, right? So this is 0 to 1 second. This is zero to 1 second. Okay. At 0 time, this is time. Okay. Anything that you see over the dot mark is the time. Okay. I wrote it below here, but usually we write on the top of the dot mark. Okay. So these are the times. So at 0 second time, my position is here at 1 meter. These are all in meters. And in the next instance of time, in 1 second time, my position is here, and my position is here. So the position of B is here. So that means B is changing its position faster than A. That means it's moving faster, or its speed is greater. Okay. So speed is denoted by letter V. Okay, that's the speed. And speed is given by rate of change of position. Rate of change of position is delta x over delta t. Now we talked about two types of motion. One is uniform motion, and the other one is non-uniform motion. So in uniform motion, like here, so in each second time, the distance travel is same, right? So it travels d, the change in position is d here, change in position is d here, change in position is d here. So in each second time, 1 second time, 1 second time, 1 second time. So from here to here is 1 second, from here to here is 1 second, from here to here is 1 second. Okay, so change in position for each second is 1 meter, or let's just say d. Or generally, in general way, you can also write in t time from here to here is the time interval delta t. It travels distance d. From here to here, time interval is delta t. It travels distance d. So d over delta t. Sometimes delta t is just written t, okay, instead of writing delta. So this is for uniform motion. When we are talking about uniform motion, we can just divide the distance by time. Okay, that gives us the speed. Okay, the meaning of this one is same distance covered in same time interval. Okay. Now we have also non-uniform motion. In case of non-uniform motion, we'll have different d's for different time. Okay, so here we can see 0, 1, 2, 3, 4, 5, like that. So in the first second, let's say it goes from here to here. Okay, 1 second time. In the next second, it goes here. In the third second, now it travels like that. And in the fourth second, let's say it's here. You see, in the first second, it travels that much distance. In the next second, it travels that much distance. In the third, it travels that much distance. So the distance traveled in each of the seconds is different. Okay, so that means we just use this formula for non-uniform motion. So different distance in different time interval. So for non-uniform motion, speed varies, okay, or speed changes, whereas for uniform motion, speed is constant. Okay. Any question about uniform and non-uniform motion? It's pretty straightforward, I think, because this is basic knowledge that you might have seen in high school also. If not, I mean, this would give you a basic idea about what these things are.
So is the formula going to be the same?
Yes, formula is same, but in case of uniform motion, we just write this as the definition of speed. So whenever you see uniform motion, write speed to be d over t. But when you are talking about non-uniform motion, you cannot write that. Okay, you need to write this one. So when we are talking about non-uniform motion, at each instant you will have different speed. For example, from 0 to 1 second, from here to here, our speed is 1 meter per second because it traveled 1 meter in 1 second. From here to here, what's the speed? Distance over time, so delta x over time. What's the speed from here to here? Speed is, okay, so let me show you how you find the speed. Speed is final position minus initial position, okay, that's the formula for delta x, and delta t. What's our final position between 1 and 3? 3 is the final position. Initial position is 1, okay, we are considering between 1 and 3, so 1. And what's the time interval from 1 to 3? 1 second, yeah. So from here to here is 1 second time. Okay. The total time from here to here is 2 seconds, but this is just 1 second. Each interval of this is 1 second time. So 1, that is 2 meters per second. Okay. So here it's 2 meters per second. Likewise, from here to here, it's again 1 meter per second. Okay. Distance or position, change in position over time. And from here to here, from 4 to 7, what's the speed? Change in position is 7 minus 4, which is 3, and time from 4 to that is 1 second. From here to here is 1 second. Okay, that's 1 second time. So 3 meters per second. You see, at each and every instance, the speed is changing. So each of these speeds are called instantaneous speed. Okay. So these speeds are called instantaneous speed. So that means speed at different instances. Whereas in this case, in uniform motion, speed is always same, okay? But in non-uniform, it is different, okay? I think we are almost out of time, so I will stop at this point, and we will continue this in the next lecture. And in next lecture, we will also do some worksheet problems. We'll have our in-person lab this Friday and Thursday, so please come to the lab if you have lab this Wednesday or Thursday.